Take it away. So the next speaker is Berfin Simsek. She's a PhD student in Wolfram's lab, jointly advised by Clement.
Thanks for the introduction. Oh. So do you see my screen fully?
Actually, no, we are seeing the presenter's screen and not the presentation screen.
Okay, this should work better.
Now this is okay.
All right. Yeah, I'm quite excited to be giving a talk today here after two really great talks. And I think in my talk, we will have the theory part, but really for neural network landscapes this time. So it should be somehow in between the first two talks that we heard today. So I'll talk about the geometry of neural network landscapes, symmetry-induced settles, and global minimum manifold. And this work is in collaboration with François, Valentin, Flavio, Francesco, Arthur, Johanne, and my supervisors, Clement and Wolfram. So the talk will be largely based on our ICML paper in 2021, but I'll also have some pointers to our ongoing work. So I'd like to start by asking a general question about the loss landscapes in overparameterized neural networks. How rough is it? So is it very rough, like in this picture, in the sense that we have a huge number of saddle points in comparison to a smaller amount of global minima points? This kind of error landscapes are typical for random error functions, especially in high dimensions, like random Gaussian processes or spherical spin glasses. Or does it look more smoother, like in this picture, in the sense that there are some settled points, but not too many to avoid convergence to a global minimum point? And recently, it's been shown that very wide neural networks exhibit this kind of smoothness in the sense that gradient descent with typical initialization, convergence to a global minimum reliably, and the requirement on the width is either infinite or polynomial in the number of training data points. So in this talk, I'll argue that for mildly overparameterized networks, the landscape is very rough, whereas for vastly overparameterized, it's going to be more smoother. And I'll argue that the roughness gradually decreases with overparameterization. And what I mean by roughness today is that it is the ratio between the number of saddles to the number of global minima components. So the big question for me today is the following. Can roughness give an insight on how much overparameterization is sufficient for reaching a zero-loss solution beyond worst-case guarantees? And to tackle this question, I gotta first introduce some structures on the saddles and the global minimum manifold. So I'll do this in the first two sections. And for the saddles, we will try to answer if there is a hierarchical organization between the saddles of neural networks. In particular, how many affine subspaces of saddles are there? Moving on to the global minima section, we will precisely describe the geometry of the global minimum manifold in terms of its number of components and connectivity. So first, we start with the symmetry-induced saddles, the construction and the number of components. Let me introduce you to setup first. We consider any input-output function y with arbitrary input and output dimensionalities, a differentiable single sample loss that maps to non-negative values, and it is zero if and only if the two inputs match, differentiable activation functions, and any input data distribution, either discrete or continuous. So this is a super general setup. For this setup, we consider a loss function that is an average over the predictions between the true labels. And the predictions are parameterized by a neural network with one hidden layer and R neurons in this case. So this is the loss on R neurons. Here and there, I'll be using these kind of cartoons to illustrate what I'm talking about better. And WIs are the incoming vectors, AIs are the outgoing vectors, and each one of the neurons are composed of the combination of the outgoing and incoming vectors. So here, each color is different from each other, representing different neurons. And this difference is actually important, which brings me to the definition of an irreducible point. So that is to say, no two incoming vectors are equal to each other in a network point. So I cannot represent the same function by a narrower neural network, in other words. Now I'm ready to state the main theorem for this section. So we consider an irreducible critical point of a network with width R, and it achieves a certain loss. And this network is parameterized in this way. Now considering a neural network with larger width M, in this landscape, there are affine subspaces of critical points at the same loss. And the dimensionality of these subspaces is M minus R. And I can give the precise number of such affine subspaces. So I'm going to break down this theorem into pieces. So first, I would like to look at the simplest case when M is only one neuron larger than R. And we will really construct an explicit line of critical points. So remember that I had started from a critical point with R neurons. So having these R neurons, I'll just take one of the neurons and split it into two pieces in a particular way, just by duplicating the incoming vector and splitting the outgoing vectors in two pieces such that the summation is still fixed. And we can see the split in the cartoon as well. So the two neurons together represents the same green neuron. With this split, the network function remains the same because the summation of the neurons did not change. But to argue that these are critical points, I also have to talk about the first order derivatives. And indeed, under this split, the gradients remain at 0. And this kind of split was explored way before, first by Fukumuzu and Amari in 2000, and also by some recent work. But building upon them, we also studied the number of such affine subspaces. And just to give the intuition first, so we can, once we have a line of critical points, we can also consider the permutations of such lines just by permuting the neurons inside the neural network. So here, this parameterization gives a line of critical points in the parameter space. And by permutations, I end up getting different lines that are not intersecting with each other. But actually, I would like to talk more about the number because we will get back to this later for the roughness arguments. And I would like to work out the number for the general M case. So we start from a width R network, and we can either split the first neuron or the second neuron, and each one of the splits gives a line of critical points for the width R+1 network. Moving on to R+2, now we can split the first neuron for once more, or we can take another neuron and split it into two pieces, and so on. So each split represents a subspace with dimensionality M minus R for general M. So in the case of 2, we have 2 free parameters here and 2 here, and so on. One could convince herself. And I would like to ask how many splits are there for general M? And this is equivalent to arranging R incoming vectors in M slots. So in the time of writing the paper, we had this more intuitive but less compact formula for the number of such affine subspaces, that is G. So we start from a critical point with R neurons and replicating the first neuron for K1 times and the Rth neuron for Kr times. We end up getting a subspace like in here, but then we should also consider the permutations corresponding to each one of the partitions with these numbers K1 to Kr. And also we have the condition that Ki should be bigger than 1 because we have to use each neuron at least for once. As it turns out, after the publication, we figured that these numbers are closely related to the Stirling numbers of the second kind, which are well studied in enumerative combinatorics. So I'll give another representation of this number in terms of Stirling numbers of the second kind. So we start from a width R network. Now we gotta find, we gotta ask how many ways there are to position R incoming vectors into M slots. So that is the number of surjective functions actually from a set of R items to another set of M items. And this is represented by this formula. But then we also, for each partition, we have R factorial ways of coloring the partitions. So choosing which neurons to position in each one of these buckets. And that gives another representation of the G number. To summarize this section, so we call such critical points in a network that originated in a narrower network symmetry-induced. And the symmetry-induced critical points form an explicit and huge number of affine subspaces. But so far we discussed the first order gradients. So what about the second order derivatives at these critical points? And I've been actually hinting to this at the title because I was talking about the saddles. So in particular, the question is, are the symmetry-induced critical points strict saddles, non-strict saddles, or local minima? Just for a quick recap, strict saddles, for the losses that are twice differentiable, strict saddles are those with at least one negative eigenvalue in the Hessian, and the other two groups are have such Hessians that with all eigenvalues non-negative, and in particular non-strict saddles, if you follow the zero direction in the eigenvalue, then it should the loss should go down. So that's why still it is a saddle, but it's not a strict saddle. So now I'm ready to state the theorems for this part. So in the ICML paper, we were able to show if we start from a strict saddle point, then under this particular mapping, in the larger networks, we end up having strict saddles too. And the difficult thing was like, what happens if we start from a local minimum or a non-strict saddles in a smaller network? What happens under this mapping? We go to critical points, but are they still strict saddles or now local minima? That may be problematic. And it turns out they are all strict saddles under very mild conditions. So we were recently able to prove this with explicit conditions. And in short, all symmetry-induced critical points are strict saddles, except for a few pathological cases. So hence the title Symmetry-Induced Saddles. And I want to finally talk about the hierarchical organization of such saddles. We can now fix M and apply the theorem for all R smaller than M. And I'll apply this in a cartoon. So we take a critical point in a network with one neuron, and this point achieves a certain loss. And applying the theorem, we see that it induces an M-1 dimensional affine subspace of saddles, and the G number returns 1. So there is only one such affine subspace. So this is not a very interesting case, we could say. But we can also apply it for any arbitrary R. And we start from a minimum, apply the theorem, we go to M-R dimensional affine subspaces of saddles with a particular number, and we have an explicit formula for this combinatorial number. And we can do the same thing. M-1 case is of interest because we go to now lines of saddles, and the formula opens up into this simple form. And we can do this for all sizes smaller than M. So we end up getting this layers of saddles in a network with M. I'm now ready to move on to the global minima manifold section, and we'll discuss in particular the number of components and connectivity. So we discussed one particular invariance, but I'm wondering if there are further invariances preserving the network function. So again, starting from an R neuron network, we are enlarging into an M neuron network. So what we discussed was the neuron splitting. That was to duplicate an incoming vector and split the outgoing vector into two pieces. But now we can add some gray neurons actually, and those represent zero neurons. So these could be the neurons with arbitrary incoming vectors and zero outgoing vectors. So we have two such neurons in this case, or zero neurons could imply two arbitrary incoming vectors such that their outgoing vectors sum to zero. So they just cancel out each other, and we end up getting the same network function. And we can have these new invariances because we don't care to preserve criticality anymore. It's sufficient to preserve the network function in this case. If the narrow network reaches a low loss epsilon, so does the larger network in this case. But I didn't talk about the global minima manifold yet. For that, I want to have a further assumption. That is that the labels are generated by an irreducible teacher network with R star. So the input-output function Y is parameterized by a teacher, but this teacher can have any input or outgoing weights, and also arbitrary number of outgoing nodes. And in this case, the over-parameterized networks are those with larger widths M than R star. So with this, we are ready to state the main theorem for the global minima manifold. In a landscape of an over-parameterized network with M, there are affine subspaces of zero loss points that are connected to one another, and each affine subspace has a dimensionality at least M-R star. And we have an explicit formula for the number of such affine subspaces in terms of R star and M. That is a number T, and it can be decomposed in terms of the number that we already know, G, and another combinatorial summation factor in terms of G and some coefficients. And with that, I'm ready to define the global minima manifold. So it is the union of such affine subspaces that are described in here of zero loss points. But I would like to illustrate this theorem in a simple setup to get a bit better intuition. For the case when we have only a little bit of overparameterization, that is only one more neuron than the teacher size, and we consider a teacher with 2 neurons, and then the student has 3 neurons now, the T number returns 12 affine subspaces. And in this case, each one of the subspaces is represented by either green or blue, and each one of them are connected to another affine subspace. And the union of all such affine subspaces is a connected manifold, because now if I start from this red point and I want to go to this other red point, I see that I can connect these 2 points with a path, and actually it's a piecewise linear path in this case because the components are affine subspaces. And this kind of connectivity was explored by a large body of super great work. But now the question for us is, are all zero loss points inside this global minima manifold? Because this theorem was only about like what the global minima includes, but is it all there is, or do we have other zero loss points in the landscape? For that, I have some further assumptions. So now if we assume that the input data distribution P has full support and the teacher configuration is unique up to permutation, then we are able to give a positive answer. So for some activation functions, with some technical assumptions that I'm happy to discuss if there are any questions on this later on. And for input data distributions with full support, then we are able to show that all zero loss points in an overparameterized networks are inside this global minima manifold. And for example, soft plus satisfies this technical assumption, and the theorem, from the way that the theorem goes on, we see how to generalize it for the other activation functions like sigmoidal or 10H. To summarize the section, for full support input distributions, all zero loss points are inside the global minimum manifold. And the global minimum manifold is composed of an explicit and huge number of affine subspaces. So now we go back to the main question in the introduction. That is, can the comparison of the number of components of the global minimum manifold and the number of subspaces of the symmetry-induced saddles be a determining factor about whether the gradient dynamics reaches the global minimum reliably or not? So far we discussed nothing about the gradient dynamics at all, and it's only about the landscape. And indeed, theoretically, we are not going to address the dynamics, but we are just curious, like if this kind of roughness estimate of the landscape that is about the number of critical points can give an idea about what the gradient dynamics is going to do. And for that, we consider a minimalistic setting that is for all the underparameterized networks. There's exactly one minimum up to permutation and no further irreducible critical points. So we've already had set the teacher at size R star. And for all the networks with smaller widths, we assume that there's only one minimum up to permutation. And we know that when we now consider an overparameterized network of width M, there are the symmetry-induced critical points induced by these irreducible minimum of the underparameterized networks. And there are the components of the global minimum manifold coming from the teacher size. So in this minimalistic case, having the definition of roughness as the ratio between the number of saddle components to the number of global minimum components, this is exactly equal to the summation of the number of symmetry-induced saddles divided by the number of global minimum components. And actually, we wanna get an understanding of how this roughness measure behaves with overparameterization. For that, we implement this ratio for the teacher size of 30. So we consider the overparameterized network starting from 30 up to 70. And we see that this roughness measure gradually decreases with overparameterization. And this is just an implementation, but we also have some limiting behavior for two cases. For the case with mildly overparameterized, in particular when M is just a little bit larger than R star. So in this case, K and H are fixed, and we consider the limit R star goes to infinity. Then the number of one particular group of saddles divided by the number of global minima components is already polynomially large in the feature width, and this is a constant factor in front. So the number of saddles really dominate the global minima components for general R when for R star goes to infinity. Sorry. And the second limit is for large M, when that is much larger than R star. And for that, we now have to consider all the symmetry-induced saddles. And actually, we are allowing arbitrary multiplicity factor here. So maybe there's not only one type of irreducible critical point in an underparameterized network, but mk of such points. And in this case, the number of the symmetry-induced saddles divided by the number of global minima components is upper bounded by a factor that is exponential in M, and this goes to 0 as M goes large. So it's really the global minima components dominate symmetry-induced saddles for very large M. So illustrating these two limiting cases in this figure, you see that for slight overparameterization in the mild regime, the number of saddles dominate, and the vice versa in the best regime. So far I've been discussing the shallow case, but the gist of the argument really comes from the permutation symmetry of the hidden layer neurons. So we can generalize it for the deeper neural networks just by applying the same trick for our favorite hidden layer. And in the deep case, and in that case, applying this trick for every single hidden layer, these factors get exponentiated. So the roughness itself gets bigger in the mild regime and smoother in the best regime. So indicating for the deep case, the mild case is even more rougher compared to the best case. And I'd like to discuss some empirical results. First with our toy setup, and it's a teacher with 4 neurons with a dense two-dimensional input. And we consider 2 student networks that are overparameterized, one with 5 neurons and the other one with 45 neurons. And for the case of the vastly overparameterized student, we see that all typical initializations, so we had 50 of them, convergence to a zero loss solution. And also, but for the slight overparameterization case, we see that a fraction of initializations, and we have 14 of them in this case, fail to find a zero loss solution. Although we have an abundance of solutions in this case, because we know that the invariances of the teacher are preserved in the student with 5 neurons as well. And then we go to the deep teacher case. So the teacher has 4 hidden neurons in all 3 hidden layers. And we consider a student that is mildly overparameterized with 5 neurons in each hidden layer, and another student that is vastly overparameterized with 20 neurons in each hidden layer again. So the vastly overparameterized student finds zero loss solutions always for all the initializations that we consider. But now the mild overparameterization fails to find any zero loss solutions at all, although it is possible to represent such solutions in the deep case as well. So we have a bigger fraction of failures in this case. But then going back, like, do these points correspond to symmetry-induced saddles themselves? But it can't be, because the gradient descent and variance provably escapes strict saddles, and this is proven by several works. But then, so we were wondering the causes of such failures, and we ended up managing the show. Like, there are some cases, there are some assumptions on the strict saddles, under which, like, there's always a local minimum near a strict saddle in some cases. So this is an example of such a case, actually. And this purple point here is a strict saddle. And so because of some of its properties, we can always show that there's going to be a local minimum around it. And yeah, I clicked on this figure a little bit earlier than I wanted. But this is a less toy experiment, but still a toy-ish experiment on MNIST. So we are training a teacher network to learn the MNIST data set, and this network has size 30. And once this network is fitted, we are changing the labels of the MNIST data set from the one-hot encoded labels to softer labels that are the logits of the teacher networks, basically. So we create a teacher that is based on the MNIST input images, but we just change the labels. And with this, we can study the amount of overparameterization. So we see that for a small amount of overparameterization, we are almost never able to reach a zero-loss solution. And this is the mildly overparameterized case. But once we increase the overparameterization, and in this case, it's by a factor of 4, we are able to reach a zero-loss solution in all the cases. And yeah, there's a small optimization problem in these points. So that's why I'm able to say that for all cases, we are able to reach a effectively zero-loss solution. And this brings me to my conclusion slide. So we show that the neural network landscape exhibit families of symmetry-induced saddles. And in overparameterized nets, the zero-loss points form a certain number of affine subspaces that are connected to one another. Thus, the union of such affine subspaces gives a connected manifold that we call the global minimum manifold. And comparing the scaling of the subspaces of symmetry-induced saddles and the zero-loss subspaces, we find at the beginning of overparameterization, which is what we call the mild overparameterization, number of symmetry-induced subspaces dominate that of the global minima subspaces. So the landscape is rough, and it is difficult to find the zero-loss point. With vast overparameterization, the ratio flips around, and the number of global minima subspaces dominate the number of symmetry-induced saddle subspaces. The landscape is smooth, and it's easy to find a zero-loss point, consistent with the literature for overparameterized neural networks. And I would like to finish with some open questions. So we don't know yet if there are new irreducible local minima emerging with overparameterization. And so having this knowledge of neuron redundancies on the global minimum manifold, can we leverage this for structured pruning? Finally, and this is the one that I'm most excited about, can we identify how much overparameterization is needed for reliable convergence beyond worst case guarantees using this roughness information? Thanks a lot for your attention. I'm happy to take questions. I hope I didn't cross the time limit.
No, perfectly on time, Berfin.
Okay, cool.
Okay, so maybe we take first questions from the audience. I also have some questions. So great talk.
Thanks.
So I think Yihan has a question. Do you want to read it or do you want me to read it?
I can also go ahead.
Okay,
it. So he is asking, what does the theory of roughness say about the spin glass models and the performance of SGD type algorithms you mentioned at the beginning, with a particular model whose landscape is known to be complicated? Yeah, this is a very good question, actually. And I have to say, at a high level, we were inspired by this classical statistical physics models, where they really like to study this number of saddles, number of local minimum, and so on. So I think it's really interesting. So I can't just go ahead and say our theory is going to say something about the more statistical setups, because our arguments are really geometrical in nature. But so they are really linked with each other, these two setups. This is all I can say at the moment, I think.
okay. So thanks for the great talk. So first, are we married to non-convex optimization? There are some convexifications of these neural network training problems that give you a global optimum with even mild number of data points plus one kind of widths. What is the relationship of some of these analyses with maybe those convexifications? Do you have any connections you can make?
Yeah, I guess I
to Mert Pilancı's work.
Yeah. So yeah, I think those works are really in the super vast overparameterized regime.
No, it's
no, not really.
No, it's very tight.
Yeah, so I don't know the details of this work actually, so I would be a bit scared to make a lot of comments. But about convexification in general, I mean, what I can say that these symmetry-induced saddles are always there, even if we infinitely overparameterize the network, because yeah, the invariances remain for this model that I described.
That is correct, but you also have this notion of irreducible networks in terms of the width, right? So if you look at these lifting of neural networks with respect to their width, maybe you can solve a convex program. I'm not saying it's an easy thing to solve, right? Even if it's polynomial, it can be very expensive. Then what you're describing actually is very interesting, to prune the networks into this irreducible network. So that is also maybe in a later paper by Mert. So I think that may be relevant to some of the things you're doing here. And in addition, what you're doing seems to be very fundamental to what people have been doing maybe in 70s, even to like some manifold theories where you look at, so some people, I mean, we've also looked at these avoidance results with algorithms, and there you need to establish maybe the subspace dimension so that SGD, for example, can avoid saddles. There, the center manifold theorems come in, and what you're doing is maybe showing that some of these saddles become meager as you increase overparametrization, and that some of these nice points you're interested are become generic. So if you can kind of connect to that kind of theory, that would be fantastic, actually.
Yeah, I want to just clarify one thing about the saddles, because at first, at the time of publishing this paper, I was a bit confused maybe, and I was thinking maybe the cause really of failures in mild overparametrization is the symmetry-induced saddles. Mm-hmm. Because I didn't know if they were strict saddles or non-strict saddles. We didn't have the second order derivative information, but now we know for sure that they are all strict saddles. So normally SGD or GD or any variant that your favorite optimizer should be able to escape these strict saddles. Yeah. But then we are figuring out now, and actually the intuition comes from the dynamical systems with 5-4 models and similar models, that in some cases there are local minimum near strict saddles. And for that, we have to look at the third and fourth order derivatives. And it could be the case for neural networks, but we are looking into this basically.
I think resonance have rich saddles that, so some of the geometry is very tricky here and subtle. It's good. What the things you're looking at are very interesting. Yes.
Thanks.
Okay, any other questions for Berfin?
There's a question in the audience. I'll just take it, I think. So do you think that it might be the case that the instability from the previous talk for the case of CFAR or ImageNet comes from the fact that the networks don't have enough parameters? Yeah, this is but yeah, it's again a complicated question for me because I'm afraid it's not my expertise exactly. But as Jonathan said in the previous talks, even if he looked at the wider networks, he wasn't able to find linear mode connectivity. But I can say, okay, what I am showing here. Oh no, I will have to go here. So in this case, the global minimum manifold and the yeah. So if you split two initialization at this point, for example, we could expect that they go to the same affine subspace of zero loss points. And then Jonathan would call these points linearly mode connected. But if you initialize farther away from them, then one of the points is going to go to one of the spaces, and the other one is probably going to go just to another subspace. So I think this is a link between these two works.
Okay, I think Joan has a question as well.
Thank you, Berfin, for a very nice talk and very nice results. So I have a question that, so it seems that here you try to classify saddle points or stationary points in terms of the index, right? Just like looking whether they are saddles or not, strict or not. Do you have a sense whether you can quantify, you have like kind of a smooth, like a soft version of that takes into account the learning rate? So in other words, this related to this like edge of stability that I talked about, where there's this phenomena that the learning rate of your algorithm is somehow giving you a lens on what are the kind of the eigenvalues that you are actually sensitive to, right? In the sense that you can think about like this kind of like oscillatory phenomena that comes from finite discretization that allows you potentially to jump from one basin to the other, or in particular to to do something that that it's not felt, it's not seen at continuous time. So do you have a sense of whether the learning rate has a role to play in this classification of saddle points?
Yeah, I have to say it's something that I haven't thought about so far, learning rate in particular. But yeah, okay, I can still give an answer, because if the problems are really the local minimum and they have really this basin of attraction, and I'm not sure if you can escape this with just a small increase in the learning rate. But if you really further increase it, then you can jump out of the basin and jump between basins. So yeah.
Yeah. Okay. Thank you.
There is another question.
Hi. I have a question about the roughness you defined by the number of saddle point over the global minimum. So my question is, does it uniform, this roughness index is uniform to index the landscape, or in different initialization parts, maybe this roughness can be very different? For example, in linear regime like NTK, the initial parameters can exponentially goes to the global minimum, but in near field maybe slightly different, or maybe in the smaller initialization, maybe it can go to some like saddle point local minimum maybe. So I'm trying to understand that this roughness index characterize the whole landscape or just a part of the parameter space.
Yeah, that's a good question. So for me, it's really it really is distributed all over the landscape, because also we have the lines or the subspaces that I'm talking about here are permutations of each other. So they really cover around all the landscape, we could say. And about the part of the initialization scale of the question, and yeah, I think I would like to push it to Arthur's talk tomorrow, because he's going to talk about, I think, this point. And in our paper together for linear networks, just as a small teaser, maybe for small initialization, we observed that the saddles become relevant. So it's similar to the mean field regime. But yeah, more about that later tomorrow, I think.
All right. So, Jean, you have another question, or?
Sorry, I forgot to lower my hand. Yeah.
Okay. All right, so maybe let's thank all the speakers, and this concludes the session.